Fluid dynamics. Take one. All right, one important difference between static and dynamic or moving fluids is that a moving fluid can exert a force parallel to any surface over which it flows. So if I were to draw, let's just say a pipe, just any old tube, and I've got a fluid flowing through it, there is a force on that pipe. So the fluid exerts a force on the pipe, force in from the fluid on the pipe. So, and that's just the way it is. So there's a fluid that travels through, it's rubbing on the pipe basically, and so there's a force from the fluid on the pipe. Well, according to Newton's third law, that requires an equal and opposite force from the surface on the fluid. Every action force has an equal and opposite reaction force. So the force of the pipe on the fluid is called a viscous force. So it's really the same thing as friction between solids. So when your tires are, you slam on your brakes and your tires are rubbing on the road, that force of friction is equivalent to a fluid rubbing on the side of a pipe. So the pipe it's a resisting force. It basically causes the fluid to slow down. Okay. All right. Now flow can be either laminar or steady. Or unsteady. We don't have any fancy physics words for unsteady flow. We could probably make one up. Laminar or precious flow, right? Okay. An ideal fluid is incompressible and undergoes laminar or steady flow and has no viscosity. It's the ideal physics world where there's free candy in the van. Yay. Okay. Now, we use these assumptions to model the behavior of fluids. So ideal fluids, it's the perfect physics world where everything works the way it's supposed to. And that's what we use to model the behavior of fluids. Okay, continuity equation. Let me get this thing out of the way because it's just kind of getting there. Basically, if we have a pipe that widens, so we have a pipe that widens here, we're looking at a couple of things. The mass passing through one section, and that first section is right here. So we have a mass passing through one section must be equal to the mass of the fluid passing through another section anywhere in the pipe in order to maintain a laminar or a steady flow. So basically you could kind of think about this as conservation of mass. So the amount of mass in this first section has to be equal to the amount of mass that's moving through the second section. So page 332 and 333 derives the equation, but in the end what we get is the continuity equation. So A1 V1 right here, A1 V1 is equal to A2 V2, and if I refer back to the picture here, A1 V1 has to be equal to A2 V2. And it's basically conservation of mass. Let me write that in here. Conservation of mass. Like I said, the book has a good derivation of it, so I'm not going to repeat that here. Now, what this means practically, conceptually, is that the larger the cross-sectional area, the slower the fluid moves. And if you think about that, you've seen that before. Anytime you've looked at a river or a stream, the wider the river, the slower the water moves. I mean, just, you may have seen the Mississippi River. It's huge. And the wider the Mississippi River, the slower the water moves. The narrower it is, the faster it moves. Okay, moving on. The Bernoulli effect. Well, let's say that 10 times fast. Bernoulli. Fluid flows faster where pressure is lower. Now, let's think about that. Fluid flows faster where the pressure is lower. How does that make sense? Okay, that's one of those big questions in physics that we will answer right now. Now, here's how it works. Fluid moves from high to low pressure. think that's pretty straightforward. I don't think I need to convince you of that because there is more pressure behind the fluid than in front of it. That creates a net force causing the fluid to accelerate as it goes from lower to higher pressure. Sorry, from high to low pressure. My bad, I didn't write the word high in there, so I didn't see it. So again, fluid moves from high to low pressure. As it moves from high to low pressure, there's more pressure behind it, which means more force. And so the net force is pushing it into the lower pressure. And that is why, let's backtrack, that is why fluid flows faster where the pressure is lower. Okay, I think you guys got the concept here. Now, this turns into an equation. It's long and complicated, and I think if I find it in the book here, I can give you the page number for it. But in the end, let's see, Bernoulli. This is on page 335. 335 in the book. So P1 plus rho GY1 plus 1/2 rho V1 V1 squared, and then you have the equivalent with the second position. Now P is pressure, rho is density of the fluid, G is the acceleration due to gravity, which you guys know that already. Y is the height above some arbitrary point, and V is the speed of the fluid. Now, this form of the equation that I've given up here in green is useful for book problems because the book does use this version of the equation to solve some of the problems. But the equation that you get in your answer sheet or your equation sheet, the stuff that you're going to need for the AP test looks like this. So P pressure is equal to rho GY plus 1/2 PV squared, and that is constant. I want you to think about this in terms of energy. P is change in pressure. Think gauge pressure. And rho GY is basically gravitational potential for the fluid. And then 1/2, let me just mark because I'm looking at the screen and you guys might not see what I'm looking at. And then 1/2 rho V squared is pretty much the kinetic energy of the fluid as it flows. And so what I want you to do is think about this equation as an expression of conservation of energy. That if you add up all three of these, the energy is conserved. The amount of stuff you have is the same no matter what. And this is important. This is coming back to our assumptions of an ideal fluid. There is no outside force to change the amount of energy. So the Bernoulli equation is an expression of conservation of energy. It's just the energy of the fluid. So pressure, gravitational potential, and kinetic energy. That's the important part. So conservation of energy. Total energy is constant in the absence of outside forces, otherwise known as viscous forces. All right. Now, the last thing I'm going to mention on the video, there's a very useful video specifically on Bernoulli's equation, and we put the link on the homework page right underneath the link to this video. And so it's a useful thing. It's from an AP Physics site that we found, and it goes through it with better graphics than I can do here, and with checkpoints along the way. So I would really recommend watching this video to get better insight into Bernoulli's equation. And so they do have at certain points they'll stop and ask you questions about the video so that it's a check-in and it reinforces the ideas. So I think we've got fluid dynamics covered. It's another Ninja Squirrel production.